By now you may have heard the term, Internet of Things. That sounds interesting. But, what does the Internet of Things actually means? IoT is an evolution of mobile, home, and embedded applications that are being connected to the Internet, that integrating greater compute capabilities, and using data for analytics to extract meaningful information. Billions of devices will be connected to the Internet, and soon hundreds of billions of devices will connect with each other. They can become an intelligent system, and when these intelligent devices share data over the cloud and analyze it, they can transform our world in countless ways, whether it is improving medical outcomes, creating better products faster, with lower development costs, or optimizing energy generation and consumption. Here is an example of the big picture. Imagine an intelligent device such as a smart traffic camera. The camera can monitor the road for congestion, accidents, and weather conditions, and communicate that status to a gateway that combines it with data from other cameras, creating an intelligent citywide traffic system. Now imagine that intelligent traffic system connected to other citywide transportation systems. For example, let's say the intelligent traffic system detects massive congestion due to an accident. That insight can be sent to the citywide transportation system. The system then analyze and derive optimal routes around the accident, and send those instructions to the city's digital signage system to guide drivers around the accident. So these are a very few example of the application of IoT project. So how does IoT device connect to the Internet? Embedded systems are already playing a crucial role in the development of the IoT. In broad strokes, there are four main components of an IoT system. The thing itself, the device. The local network, which include a gateway, which translates proprietary communication protocols to Internet protocol. The Internet. Back-end services such as enterprise data systems, or PCs and mobile devices. Let's take a smart home as a typical case for an IoT system. The first networking technology candidate for an IoT device is Wi-Fi. A smart home would need a large number of connected sensors and actuators scattered over a wide area, and a wireless technology would be the best fit to connect. One of the major IoT enablers is the IEEE 802.15.4 radio standard, where it provides the basis for low-power systems. By using wireless, it will connect all the devices to the gateway, where it will translate the communication protocols to Internet protocol. Next, IPv6 is typically used for IoT applications over legacy IPv4 addressing, as the current IPv4 standard faces a global addressing shortage, as well as limited support for multicast, and poor global mobility. IPv6's addressing scheme provides more addresses and mobility. With IPv6, it is much simpler for an IoT device to obtain a global IP address, which enables efficient peer-to-peer communication. If your goal is to remotely control devices, or otherwise transmit data over the Internet, then you need IPv6. Next, due to too many IoT devices, the router will function as a DHCP-v6 server, which is used to automatically assign IP addresses to any device that plugs into the network. The router would assign an IPv6 address to the IoT device that from a range of addresses given. The device shown above is assigned a dynamic address, but this could change the next time it connects into the network. For IoT device, we can either use DHCP to assign an IP, or we can use a fixed IP address, but dynamic address is preferable since it can use the IP address more efficiently. Generally, a router will automatically assign itself to the first IP in the range. This would also be the gateway IP. When the router connects to the ISP, it will be assigned an IP address, which is what is used to communicate with servers or other service on the Internet. This is a public IP address, and thus is addressable by the Internet. Be aware that this IP address will change every time that your router is rebooted, or reconnects to the ISP. The router will use the data protocols such as MQTT to send the data to cloud. The MQTT protocol enables a publish and subscribe messaging model in an extremely lightweight way. For example, for a budget home automation system that involves several sensors, MQTT would be a good choice, as it is great for implementing messaging on devices without much storage or processing power because the protocol is simple. These protocols provide two-way communication in real time. After the data is sent to the cloud, the data will be stored. The web server will retrieve the data from the cloud for analyzing purpose. After the web server analyzes the massive data, the insight and valuable data and information will send to the user via mobile application or web browser.
Next, we will use Packet Tracer 7.1 to simulate smart house automation with IoT devices. Smart house automation is one of the IoT applications which can help to reduce cost and conserve energy. Here we have a simple floor plan for a house that will be used to convert to a smart home. In this simulation, we will show how the IoT devices configure it to be remotely controlled and also how the devices are automated by the sensors. In the smart house, the areas that will be upgraded using IoT devices are living room, bedroom, kitchen, house front, garden, and garage. These IoT devices included will be configured accordingly. In this simulation, this table is used as a guide when doing the configuration for the devices. Generally, there are 3 configurations sections. The first device need to be configured is the home gateway, which acts as the control point of all IoT devices, and also as a connection point to outer network and in devices such as mobile phone and PC for monitoring or control the IoT devices. Typically, home gateway is a broadband router which allows the connection of a local area network to a wide area network. Secondly, the IoT devices and sensors need to be configured to connect to the home gateway. In this case, the devices are configured so that the IP addresses are auto-assigned by the DHCP. Lastly, the end devices need to be connected to the network so that the IoT devices can be monitored and controlled. In this simulation, only local area network is used. Thus, the end devices must be connected to the same network as the home gateway and the IoT devices. Now, let's start with the Packet Tracer simulation. Firstly, all the devices are arranged as shown here. We use cables to connect some of the devices to the home gateway as stated in the table. Note that fast Ethernet port is used during the cable connection. The rest of the devices are expected to connect to home gateway via wireless connection. At this stage, none of the devices are interconnected with each other. To let the devices to be interconnected, these 3 steps need to be followed in sequences. Step 1, Home Gateway's configuration. Go to Home Gateway's configuration menu. Under the interface section, go to the wireless settings. Notice the SSID is Home Gateway. As authentication purpose, we need to configure a password. In this case, WPA2PSK is used and it is mandatory to set the password with a length between 8 to 63. Upon setting the password, the encryption is AES by default. Step 2, IoT devices set up for IP address allocation. The configuration for IP allocation is different depends on the connection method. In this simulation, we have 4 devices connected to home gateway using cable connection. The rest are using wireless connection. For the devices using cable connection, the configuration goes like this. In the devices config menu, under global setting, set the IoT server as home gateway. Then under fast Ethernet 0, select DHCP for the IP configuration for the device. Once checked, there will be an IP address allocated to the device. On the contrary, for device using wireless connection, the steps are, by default, the devices only have Ethernet network adapter. Thus, additional network adapter for wireless connection is needed. To add or modify network adapter, click on the Advanced button, and IOconfig should be visible after clicked. Go to IOconfig, select PTI in W1W. Then, go to the config. Under Global Setting choose Home Gateway as IoT Server. Next, go to the Wireless 3 settings. Set up the authentication session and use the same password used when configuring Home Gateway. Upon password is set, the IP address will be allocated to the device. Notice there is a change in the Packet Tracer interface. This means wireless connection is successfully established. In Step 2, the rest of the IoT devices are configured using the method stated to be connected to the Home Gateway. Once done configuring all devices, interconnection network is established. Step 3, IoT monitoring using end devices. Now that all the IoT devices are connected to the internet, end devices can be used to monitor the IoT devices. Here we use a smartphone to connect to the home gateway via wireless connection. Once connected, we can use the IoT monitor application in the smartphone to access the home gateway. In Packet Tracer, we can find this application in the desktop tabs. This login screen will be shown. The IoT server address is the IP address of the home gateway. No modification is necessary here. The next screen is the list of devices that we registered as IoT server during configuration. This shows that the IoT devices are successfully configured for remotely controllable. Besides, it is possible to set the conditions so that the IoT devices are automated. One of the application examples is the alarm triggering if the smoke level is higher than the stated level. This can be set and simulated in Conditions section, which can be found on the top right corner of the IoT devices list. Here, we show a rule that will trigger several sensors if there is a fire in the kitchen. The action taken if the condition is met are listed here. In Packet Tracer, to simulate smoke, we need to use the old card to purposely increase the smoke level.